In the last class, we studied that the occupancy factor by transmitted message is 2 to the power negative of the term beta minus alpha times t. And this can be made as small as possible simply by increasing t. In the limit, as t tends to infinity, the occupancy factor tends to 0. This will make the error probability P e go to 0, and we have the possibility of error free communication. One important question, however, remains unanswered. The question is, what must be the rate reduction ratio, that is alpha by beta, in order to achieve error free communication? To answer this question, we observe that increasing t increases the length of the transmitted sequence, which is given by beta times capital T digits. Now, if P e denotes the digit error probability, then it can be seen from the relative frequency definition or the law of large numbers that as t tends to infinity, the total number of digits in error in a sequence of beta times t digits is exactly beta times t error probability. Hence, the received sequences will be at a Hamming distance of beta times t P e from the transmitted sequence. Therefore, for error free communication, we must leave all the vertices unoccupied within spheres of radius given by beta times t P e drawn around each of the 2 raised to alpha t occupied vertices. In short, we must be able to pack 2 raised to alpha times t non-overlapping spheres, each of radius beta times t P e into the Hamming space of beta t dimensions. This means that for a given beta, alpha cannot be increased beyond some limit without causing overlap in the spheres and the consequent failure of the scheme. Shannon's theorem states that for this scheme to be successful, alpha by beta ratio must be less than some constant, and that constant is denoted by channel capacity C s, which is a function of the channel noise and the signal power. So, Shannon's theorem says that alpha by beta should be less than C s, which is channel capacity. it must be remembered that such perfect error-free communication is not practical. In this system, we accumulate the information digits for t seconds before encoding them, and because t tends to infinity for error-free communication, we must wait until eternity before we start encoding. Hence, there will be an infinite delay at the transmitter and an additional delay of the same amount at the receiver. Second, the equipment needed for the storage, encoding and decoding of the sequence of infinite digits would be monstrous. Needless to say that in practice, the dream of error-free communication cannot be achieved. Then the question is, what is the use of Shannon's theorem? First, it indicates the upper limit on the rate of error-free communication that can be achieved on a channel. This result in itself is monumental. Second, it indicates the way to reduce the error probability with only a small reduction in the rate of transmission of information digits. We can therefore seek a compromise between error-free communication with infinite delay and virtually error-free communication with a finite delay. Next, let us investigate the problem of error-free communication over a binary symmetric channel. We have seen that channel capacity is the property of a physical channel over which the information is transmitted. We have also shown that over a noisy channel, Cs bits of information can be transmitted per channel. So, if we consider a binary channel, what this means is that for each binary digit or symbol transmitted, the received information is Cs bits, where Cs is less than or equal to 1 for a binary symmetric channel. Thus, to transmit 1 bit of information over a binary symmetric channel, we need to transmit at least 1 by Cs binary digits. This scheme gives us a code efficiency that is Cs and redundancy as 1 minus Cs. When the transmission of information is implied, it means error-free communication, because mutual information was defined as the transmitted information minus the loss of information caused by the channel noise. The problem with this derivation is that it is based on a speculative definition of information. The problem with this derivation is that it is based on a speculative definition of information. That is, information associated with the occurrence of a particular event E is given by I is equal to log of 1 by probability of occurrence of that event. and based on this definition we defined the information lost during the transmission over the channel. Now, we really have no direct proof that the information lost over the channel will oblige us in this way. Hence, the only way to ensure that this whole speculative structure is sound is to verify it. So, if we can show that CS bits of error free information can be transmitted per symbol over a channel, then the verification will be complete. Here we shall verify the results for a binary symmetric channel. Let us consider a binary source This source emits messages at the rate of alpha digits per second. We accumulate this information digits over t seconds to give a total of alpha t digits. Now, because alpha t digits form 2 raised to alpha t possible combinations, a problem is now to transmit one of this 2 raised to alpha t super messages every t seconds. These super messages are transmitted by a code word of length beta times t digits, where beta is greater than alpha to ensure redundancy. Now, because beta times t digits can form 2 raised to beta times t distinct patterns, which are the vertices of a beta times t dimensional hypercube, and we have only 2 raised to alpha times t super messages, we are utilizing only a 2 raised to minus beta minus alpha times t fraction of the vertices. The remaining vertices are deliberately unused in order to combat noise. Now, if we let t tend to infinity, the fraction of vertices used approaches 0, and because there are beta times t digits in each transmitted sequence, the number of digits received in error will be exactly beta times t multiplied by digit error probability, which is given by P e when t tends to infinity. We now construct Hamming spheres of radius beta times t P e around each of the 2 raised to alpha t vertices which are used for the messages. When any message is transmitted, the received message will be on the Hamming sphere surrounding the vertex corresponding to that message. We use the following decision rule. If a received sequence falls inside or on a sphere surrounding message mi, then the decision is mi is transmitted. Now, if t tends to infinity, the decision will be without error if all the 2 raised to alpha t spheres are non overlapping. Now, of all the possible sequences of beta times t digits, the number of sequences that differ from a given sequence by exactly j digits is given by beta t j, this combination. Hence, capital K, which denotes the total number of sequences that differ from a given sequence by less than or equal to beta times t p e digits is k is equal to summation over j is equal to 0 to beta t p e Now, if we use an inequality which is often used in information theory, the inequality is less than or equal to 2 to the power beta t entropy function, which is function of error probability, where error probability is less than 0.5. Using this inequality, what it implies that k is less than or equal to 2 to the power beta t entropy function with entropy function given as P e log of 1 by P e plus 1 minus P E log to the base 2 1 minus now from the 2 raised to beta times t possible vortices, we chose 2 raised to alpha t vortices to be assigned to the super messages. How shall we select these vortices is the next question. So, let us look at the decision procedure. From the decision procedure, it is clear that if we assign a particular vortex to a super message, then none of the other vortices lying within a sphere of radius beta t p e can be assigned to another super message. Thus, when we choose a vortex for a message say M1, the corresponding k vortices become ineligible for consideration. Then from the remaining 2 raised to beta t minus k vortices, we choose another vortex for M2. We proceed in this way until all the 2 raised to beta t vortices are exhausted. Now, this is a rather tedious procedure. So, let us see what happens if we choose the required 2 raised to alpha t vortices randomly from the 2 raised to beta t vortices. Now, if we adopt this procedure, then there is a danger that we may select more than one vortex lying within a distance of beta t p e. If however, alpha by beta is sufficiently small, the probability of making such a choice is extremely small as t tends to infinity. Let us look at this in little more detail. Now, the probability of choosing any particular vortex S1 as one of the 2 raised to alpha t vortices from 2 raised to beta t vortices is given by two raised to alpha t divided by 2 raised to beta t, which is equal to 2 raised to minus beta minus alpha t. Now, remembering that k vortices lies within a distance of beta times t p e digits from the vortex S1, the probability that we may choose another vortex S2 that is within the distance beta times t p E from the vertex S1 is given by the expression P, that is this probability, is equal to k times 2 minus beta minus alpha t. Now, we have shown earlier that k is less than or equal to twice beta t entropy function. Therefore, from this equation it follows that probability of choosing another vertex S2, that is within the distance beta t p e from S1, is less than or equal to 2 to the power minus beta times 1 minus entropy function minus alpha multiplied by t. So, hence, if you look at this expression as t tends to infinity, this probability tends to 0 if the following condition is satisfied: beta times 1 minus entropy function is greater than alpha, that is if alpha by beta is less than 1 minus entropy. Now, 1 minus entropy function is the channel capacity C s for a binary symmetric channel. Therefore, we conclude that this probability of choosing another vertex S2, that is within the distance of beta t p e from S1, will tend to 0 if alpha by beta is less than channel capacity C s. Hence, the probability of choosing two sequences randomly within a distance of beta t p e approaches 0 as t tends to infinity, provided alpha by beta is less than C s, and in this case we have error free communication. We can choose alpha by beta is equal to C s minus epsilon, where epsilon is arbitrarily small. So, we have verified the Shannon's second theorem of error free communication for a binary symmetric channel. So far in our study, the sources and channels considered in our discussion of information theoretic concepts have involved ensembles of random variables that are discrete in amplitude. Next, we will extend some of these concepts to continuous random variables and random vectors. The motivation for doing so is to pave the way for the description of channel capacity in terms of the bandwidth of a channel, channel noise and signal power. Having developed concepts of information transmission for a discrete case, we are now ready to tackle the more realistic case of a continuous source and channel. We will begin with the measure of information for a source that emits continuous signal. The material may seem heavy going at first, but we will then make reasonable assumptions about transmission of continuous signals to express the channel capacity in terms of bandwidth and signal to noise ratio. This result is known as the Hartley-Shannon law. This result leads us to the definition of an ideal communication system, which serves as a standard for system comparison and a guide to design improved communication systems. A continuous information source produces a time varying signal denoted by xt. We will treat the set of possible signals as an ensemble of waveforms generated by some random process which is assumed to be ergodic, and by definition ergodic process means that time averages and ensemble averages are the same. We will also assume that the process has a finite bandwidth, meaning that the signal xt is completely characterized in terms of periodic sample values. Thus, at any sampling instant, the collection of possible sample values constitute a continuous random variable denoted by capital X and described by its probability density function P x. Now, we have seen that for a discrete random variable x, which takes on the values x1, x2 up to xn with probabilities p x1, p x2, p xn, the entropy Hx was defined as summation of Pxi log 1 by Pxi I equal to 1 to n. Now, we can extend the definition of entropy to continuous random variable by using the integral instead of discrete summation in equation number 1. So, if we do that, we can define entropy of a continuous random variable as integral minus infinity to plus infinity of PDF Px log of 1 by Px. We shall see that equation 2 is indeed the meaningful definition of entropy for a continuous random variable. However, we cannot accept this definition unless we show that it also has a meaningful interpretation in terms of uncertainty. A random variable x takes a value in the range n delta x n plus 1 delta x with probability p of n delta x multiplied by delta x in the limit as delta x tends to 0. Now, the error in the approximation will vanish in the limit as delta x tends to 0. So, using this simplification for a continuous random variable, we can define the entropy for a continuous random variable x as h x is equal to limit of delta x tending to 0 summation of probability of n delta x log of 1 by p n delta x multiplied by delta x. This is a summation over n, and this can be simplified as limit of delta x tending to 0. We can break up this summation in two parts as follows. Log of minus summation over n p n delta x log of delta x. Now, as delta x tends to 0, this summation can be approximated by the integral, which gives the following expression p x log of 1 by p x dx minus limit delta x tending to 0 log delta x integral of probability distribution function from minus infinity to plus infinity, and this can be further simplified as. So, finally, we get the expression for entropy for a continuous random variable, which is indicated by equation number 3. So, in the limit as delta x tends to 0, log of delta x will tend to minus infinity. So, it appears that the entropy of a continuous random variable is infinite. Now, this is quite true. The magnitude of uncertainty associated with a continuous random variable is infinite. This fact is also apparent intuitively. A continuous random variable assumes an uncountable infinite number of values, and hence the uncertainty is on the order of infinity. So, does this mean that there is no meaningful definition of entropy for a continuous random variable? On the contrary, we will see that the first term in equation number 3 serves as a meaningful measure of the entropy, that is average information, for a continuous random variable x. Now, this may be argued as follows. We can consider integral p x log 1 by p x as a relative entropy with minus log delta x serving as a datum or a reference. Now, the information transmitted over a channel is actually the difference between the two terms entropy of x and entropy of x given y. Now, obviously, if we have a common datum for both h x and h of x given y, then the difference h x minus h of x given y will have the same difference as the difference between the relative entropies. So, we are therefore justified in considering the first term in equation 3 as the relative entropy of x, or sometimes it is also known as differential entropy of x. We must, however, remember that this is a relative entropy and not absolute entropy. Failure to realize this crucial point generates many apparent fallacies. Let us try to take an example to understand this. In particular, consider two information signals x t and y t. A signal amplitude x associated with the signal x t is a random variable uniformly distributed in the range -1 to +1. This signal x t is passed through an amplifier of gain 2 to obtain the signal y t. Therefore, the output of this process, which is a continuous random variable y, is also uniformly distributed in the range -2 to +2. So, we have probability distribution function for the random variable x given by half when mod x is less than 1 and 0 otherwise, and probability distribution function for y is given as 1/4 when mod y is less than 2 and is equal to 0 otherwise. Now, using these PDFs, we can calculate the relative entropies of x and y as follows. Entropy of y is equal to two bits. Now, the entropy of the random variable y is twice that of x. This result may come as a surprise, since a knowledge of x uniquely determines y and vice versa, because y is equal to twice of x. Hence, the average uncertainty of an x and y should be identical. Amplification itself can neither add or subtract information. So, the question is, why then is h of y as twice as large, why then is h of y is twice as large as h x? This becomes clear when we remember that h x and h y are differential entropies, and they will be equal only if the datum or references for both the random variable x and y are equal. Now, the reference entropy R 1 for random variable x is minus log delta x, and reference entropy for random variable y is minus log delta y in the limit. So, R 1 is equal to limit delta x tending to 0 minus log delta x, and R 2 is equal to limit delta y tending to 0 minus log delta y. Therefore, the difference R 1 minus R 2 is equal to limit delta x delta y tending to 0 of log delta y by delta x, which is equal to log of dy by dx is equal to log of 2 is equal to 1 bit. Thus, R 1, the reference entropy of x, is higher than the reference entropy R 2 for y by 1 bit. Hence, if x and y have equal absolute entropies, their differential or relative entropies must differ by 1 bit. Now, we have seen that the entropy for a discrete random variable is maximum when all the outcomes have equal probabilities. The next question is it possible to derive such relationship for a continuous random variable? We will investigate this in the next class.